This video is about a chi-squared goodness of fit test. Unlike the one proportion z test and the exact binomial test, a chi-squared goodness of fit test works even when the variable is not binary. So in other words, even if your categorical variable has more than two categories, you can still do a chi-squared goodness of fit test. So this is an example from a former student of mine. She was a marketing student and she did a blind taste test with 3 different coffee brands, 1,000 Faces, Jittery Joe's, and Starbucks. And she wanted to know whether the 3 brands might be equally popular in the population. So she actually had 23 people participate in this taste test. She has their choices, their preferred brands, but she wants to know what would happen in the long run. What if she had continued sampling people to participate in her taste test? So it says that the student is interested in whether the 3 brands are equally popular. So that's what we're going to consider in our null hypothesis. So the null hypothesis in this case would be that the proportion that prefer 1,000 faces is 1/3. Also, the proportion that prefer Jittery Joe's is 1/3. And the proportion that prefer Starbucks is 1/3. So if they're equally likely, then they all have to be equal to 1/3. And it doesn't have to be equal. You can set up other types of claims in your null hypothesis as long as they have equal signs in them. This one just happened to be a question about equally popular. So for writing the alternative in this case, we can think about what would have to happen to make the null hypothesis untrue. Right? It doesn't necessarily mean that all 3 of those proportions are different than 1/3, just that at least one of the proportions, so at least one pi, is different from the others, right? In other words, at least one of the pi's is not 1/3, not 1/3. So this is always how the alternative works with a chi-squared test. It's always two-sided, right? We're just saying that pi is not 1/3. It could be greater, it could be less. So you can always think of a chi-squared test like a two-sided test where you don't have a directional hypothesis. So the formula for the chi-squared statistic works by comparing the observed counts to the expected counts. So when we say the observed counts, we're talking about the actual data here. So the people who actually participated in the taste test. For the expected counts, we're talking about what we would expect if the null hypothesis were true. So our null hypothesis says that they're all equally likely. So if we wanted to find the expected counts for this data, we've got 23 people. And for each category, we're expecting 1/3 to be in each category. So we end up with 7.67. So notice this isn't an expected count in the sense that we know it's not going to be 7.67, right? Counts can't be decimals. It's more like on average, what would we expect to happen? So the expected count for all 3 of these categories is the same, 7.67. And then we can plug in to find our chi-squared statistic. So for each of the different brands, we're going to do the observed count minus the expected count. We're going to square that over the 7.67. So looking at this formula, you can see right away why this has to be a two-sided test, right? If you're going to take the difference between observed minus expected and square it, well, you've lost all information about which direction things go. So a two-sided test is your only real option at that point. So I'm going to keep going, do this for all of the cells, 4 minus 7.67. So that's for Jittery Joe's. And one more for Starbucks. So I've got all 3 of my terms here. And when I work that all out, it ends up to be 2.698. So usually, I'll be honest, I won't have you do this by hand. I'll have you do it with jump, but for now, I just wanted to show you how the formula works. So let's take a second and think about what that chi-squared statistic actually means. So it may help to think about what does it mean when the observed counts are somewhat close to the expected counts, or if they differ greatly from the expected counts. So pause the video for just a second here, and go ahead and fill in the blanks for these 2 bullet points. So if the observed counts are somewhat close to the expected counts, that's going to mean that these differences here are pretty small, which will end up leading to a small chi-squared statistic. This also means that the evidence against the null hypothesis is weak because the actual data is pretty close to what you would have expected if the null hypothesis were true. Whereas if the observed counts differ greatly from the expected counts, that's going to lead to a large chi-squared statistic and strong evidence against the null because the actual data was really far from what the null hypothesis told us to expect. So we're using sort of loose words here like close and differ greatly. So the question really comes up, how large is large, right? Is chi-squared equals 2.698? Is that large enough to convince us that the three brands are not equally popular? So to answer this question, we need a null distribution, right? We need to know what values would we expect to see if the null hypothesis were actually true. So pause the video here for a second and think about how you could use a simulation to find the null distribution. So think about what kind of physical object would you use, how many times would you repeat the process, and what statistic would you calculate each time. So we want to represent the null hypothesis. So we're going to use a spinner with 3 equal sections. So we're representing Jittery Joe's, Starbucks, and Thousand Faces with these 3 equal sections, assuming that they're all equally popular. And then we want to be consistent with the sample. So we're going to spin this 23 times. These are the 23 people that participated in the taste test. Each time we do that, we're going to calculate the chi-squared statistic. We want to be consistent with the chi-squared statistic we used to summarize the original sample. And then, of course, we'll repeat that many times. So unfortunately, our ISI applet collection doesn't have one for a goodness of fit test. The people who built these applets do have a bigger collection though, so I'm going to look at the Rossmann-Chance applets. And I'm going to go to their applet for goodness of fit. So I'm going to go ahead and tell you now, I'm not going to hold you responsible for knowing how to use this applet since it's not in our applet collection. Instead, once you get to the lab, you'll be doing this in JUMP. But I think it's worthwhile to show you how to do it here. So I'm going to clear this out and type in our data. So I'm going to do 1,000 faces is 9. Using some abbreviations, Jittery Joe's is 4. And Starbucks is 10. And I'm going to click Use Table. And I can see that it's got my little bar graph there, calculating each of my proportions. And the statistic that I want it to use is the chi-squared statistic. So it gives several options here, but I'm going to pick chi-square. And you can see it's calculating the same statistic that we got, just a little bit different because of rounding. So I'm going to look at my sampling options, and I'm going to tell it that my null hypothesis is that they're all equally likely. So basically, I'm telling it, use a spinner where all 3 of the sections are the same. And I'm going to look at, I think, the plot for when I do my random samples. So these red lines, these are showing what it would look like if it were perfectly equal. And even though this is coming from a spinner with 3 equal sections, you can see they're not perfectly equal. The observed and the expected are not exactly the same. And so the chi-squared statistic here came out to 1.65. So we can do more. So that one was a bigger difference between observed and expected, so you got a bigger chi-squared statistic. This one, they were almost exactly what we would have expected them to be, so the chi-squared statistic this time was really small. So these are showing all the range of the chi-squared statistics that we would get if we were really using a spinner with 3 equal portions, if the brands were really equally popular. So let's go ahead and do a whole bunch of those. So pause the video for a second here and think about it. Based on our chi-squared statistic of 2.69, do you think that we have strong evidence that the brands are not equally popular? So if we look at this null distribution, we can see that our statistic doesn't seem to be that unusual. It actually seems to be fairly close to the middle here. And we can count and see how often do we get values greater than our chi-square statistic. So 2.698. And the reason that we're counting the values that are greater is because remember, with a chi-square statistic, greater chi-square statistics means stronger evidence. So here we've got a p-value of what? 27.64%. So that means that almost a quarter of the time you would get data like ours, even if the brands were equally popular. So we found our chi-squared statistic, 2.698, and we counted all the values that were to the right, and we ended up getting a p-value of 0.2764. So what that's telling us is that even if the brands were equally popular, right, even if the null hypothesis were actually true, even if the brands were equally popular, results like our taste test, the real data that we saw, would be common. So if these would be common, even if the null hypothesis were true, then the null hypothesis is a reasonable explanation for our data, right? We don't really have much evidence here. So for my conclusion, I would say that I have not enough evidence to conclude, right? I'm not able to rule out the null hypothesis, so I can't really conclude anything. Not enough evidence to conclude the alternative, that one brand is more popular than another. So we had a large p-value. We didn't have strong evidence here. So that's the simulation-based test. So the simulation is designed a little bit different than what we're used to because it has 3 sections instead of 2. And the statistic we're using is different. We're using chi-squared, not a sample proportion. But hopefully you can see how the general process is the same. And luckily, we're going to see this general process a million times throughout the semester. Okay, so that's one option for how to model the null distribution. Another option is to use a theory-based distribution. So just like you can use a normal approximation for one proportion, you can use a chi-squared distribution to model the chi-squared statistics you would get under the null. But just like any time you're using a theory-based test, you have to check first to see if your validity conditions are met. So the rule for a chi-squared test, at least the guidelines that our book gives, is that we need expected counts of at least 10 in every category. Expected counts of at least 10 in each category. And our expected counts in this case were smaller than that. They were only 7.67, so they were less than 10, which means no, our validity conditions are not met here. So if the validity conditions are not met, then that means that it's not appropriate to use the chi-squared distribution in place of a simulation. We would want to stick with the simulation in this case. If the validity conditions had been met, though, using the chi-squared distribution works the same way as a normal approximation. You would just be shading the area under the curve to find the p-value instead of counting the simulated outcomes. Later on, you'll see examples where the conditions are met, and you will use the theory-based approach.